So please welcome.
Thank you. So, hey everyone, my name is Rafael Polanczyk. I work at the Solaris kernel performance group at Sun Microsystems. I'm based in Ireland. I'm originally from Brazil. So I'm going to talk a little bit about NUMA architectures and what OpenSolaris does to optimize performance in those machines, and hopefully kind of transmit some of my interest to you. So just an overview. My intention here is just start from scratch, considering I don't know how much you guys know about NUMA machines, if you know anything, so I'm going to start from scratch and build up until what Solaris does to optimize and what we're working towards, the new things that are coming up in the NUMA road. So where did NUMA come from? So everyone knows this picture. I think everyone knows what symmetric multiprocessing is. You have a bunch of processors and connected to a single memory, to a single bus, which is something that we are all very used to. And it's a shared memory, it's single address space. Every processor accesses the same memory through reads and writes. So it's a shared memory paradigm. Every processor, excuse me, every processor has the same latency while going through this interconnect to access memory. So it's a uniform memory access model. So it's the same latency to access the memory from whatever processor you're executing. It's good because it's traditional programming paradigm, which is, I guess, everyone is used to. But as we know, this model doesn't scale very well. So as you add processors to the bus starts to saturate and performance goes down. On the other hand, we have clusters, which are simply separate nodes connected through usually a network mechanism, which is much more scalable than SMPs, but then you have to program with a network programming paradigm. You're not just doing reads and writes to memory positions, you're doing sends and receives, so you're going through the network, and that adds a lot of latency. Plus, you're replicating data, so you have multiple instances of the OS, multiple instances of your software, and possibly your data. And then NUMA comes kind of in between those two models. You have nodes which are composed of processors and some memory or some devices, and they are interconnected through what we call the interconnect hardware. For instance, in the AMD world, this is the hypertransport. In the Intel and the Halen world, this is the quick path, which is coming out very soon. I forget what Spark calls our version. And then you have local access. Each processor can access local memory, but can also access remote memory. So it can access the memory in each other on the other nodes. But to do that, it has to go through the interconnect, which also adds latency. So it's kind of a compromise solution between SMPs and clusters. So it's much more scalable than SMPs, and it still is a traditional programming paradigm. You're still doing reads and writes regardless of which memory you're accessing. So it really is a compromise between clusters and SMPs. So just before I go into this one, NUMA is nothing new. It's been around for 20 years or so. If you go back to the literature, you're going to see stuff coming out of Stanford, for instance, the Dash and the MASH projects. But I think NUMA is becoming more relevant nowadays because it's much cheaper. I mean, if you take a look at Sun's line of multiprocessors, you take a look at IBM, SGI, Boo, every major manufacturer has relatively cheap servers which have some sort of NUMA characteristics to it. So NUMA is actually cache coherent NUMA, CC NUMA. Cache coherent because if you go back to the other slide, if you have processors accessing memory from other nodes, each processor has its own cache memory. It stores a copy of the data in its own silicon base. And when you go to access memory on the other nodes, you can have some sort of replication of data, some conflict. So you need to keep the data consistency. So, and this is done in hardware, transparently to software, at least in the current models. If you take a look at the earlier NUMA machines, this was actually done on software. So if you were programming a NUMA machine, you'd have to do it by hand, which is obviously a big pain. And this is done on hardware using some sort of DSM model, some directory-based classic DSM algorithm. So this is implemented in hardware and varies from model to model and between manufacturers. This is usually something that you can find in the hardware specification of a NUMA machine. And it's going to say how long it takes to access remote nodes. And this is something that the amount of time to access remote nodes takes into account how good this algorithm is implemented. So something I think it's important to know if you're going to look into a NUMA machine. So you obviously need some support in the software layer for this hardware. I mean, you could do it transparently, but you wouldn't take advantage of the full potential of the system. And Solaris and OpenSolaris take advantage of NUMA characteristics with MPO, which is the memory placement optimization, which is just a framework, well, not just, but a framework to provide better performance through locality awareness, which is a concept that I'm going to explain in a couple of slides. It's implemented in the kernel. This is where you can find the source for most of it. If you're interested in taking a look at the source, you're going to find out that the kernel sits on user/source/UTS. UTS stands for Unix time sharing, which is where the kernel is. Common is the platform independent layer. /sys is where all the headers files are. /OS is where most, and this is a kind of quote-unquote, most of the implementations are. And then you have platform-specific layers which sit under user/source, UTS, i86PC or Sun4, and then the same thing. So what MPO basically does is optimize a bunch of subsystems in the kernel, namely the scheduler and the virtual memory subsystems, plus add a lot of tools and APIs to observe NUMA behavior and to control and see what your application is doing. So another important word, perhaps, is called the NUMA Factor in the NUMA world. It's the ratio between local access and remote access. This is also a number you'll find both in the literature and both in the specification for hardware. And it's an indication of how performant the NUMA mechanism in your machine is. So locality awareness is also something very important in this aspect. So I've been talking about NUMA for, I don't know, 10 minutes or so now, even maybe less. But what's important about NUMA is that you have local and remote access times. And this is the key factor here. And you have to optimize performance for both your application and the kernel in the sense that you're going to try to do as much as local access as possible, but also taking advantage of the other nodes in the system. So the idea is to keep threads close to where the data device is. For instance, if you are running a thread on node 0, you want to keep accessing memory on node 0 and not go through the interconnect and access node 2, 3, 4, or whatever. You want to avoid remote access. You want to take advantage of cache warmth. Cache warmth is, if you don't know already, it's, well, take advantage of, for instance, if you have a thread running on a processor 0, the thread runs for a while, gets preempted, another thread runs. When that first thread comes back, it might have some data still in the cache, so that's cache warmth. And if you run to another node, you're not going to get a cache warmth. But we have conflicting objectives here, because we want to minimize data migration and keep things local, but now you have a big machine with multiple nodes, and we're also going to want to keep some load balance. So this is something that the kernel and all of us as developers should be aware of. The kernel is aware of, and us as developers should be aware. So most, if not every, hardware characteristic in the kernel is represented through an abstraction. Solaris implements LGroups, or locality groups, which will represent sets of resources that are close to each other in terms of latency. So each LGroup will have at least one processor and possibly some memory or some device representing the nodes. This topology, these LGroups are hierarchical. They are built up on a topology. And you have CPUs and resources on all levels of the topology. I'm going to show an example so it becomes a little clearer. But this is called the latency topology. So for instance, if you have a simple 4-node machine connected through a ring interconnect, you're going to have 4 leaf LGroups, 1 per node, and you're going to have these leaves presented in the topology. The idea is that each LGroup starts to encompass more and more resources. So at the lowest level, you have LGroups representing just the nodes. As you move farther from the leaf, you start to have intermediate LGroups. So LGroup 5 in this situation is based around node 0. LGroup 1, if you remember, was just around node 0. LGroup 5 contains node 0 and all resources 1 hop away from node 0. And the same goes on to LGroup 6, 7, and 8. So you have the topology with leaf LGroups and intermediate LGroups. And then at the root LGroup, which is the higher level and contains all the LGroups in the system, contains all the resources, and represents the highest latencies in the system, we contain all the CPUs, and it's usually the LGroup 0. So that's a topology, an example of topology for a 4-node ring NUMA machine. So okay, so you have this topology, now what? The kernel optimizes most of its subsystems, like I said, namely the scheduler and the virtual memory, using this topology. So for instance, if the scheduler wants to dispatch a thread to run, how it's going to do it? Assuming that the thread is running on node 0 in the case, and now group 1, the scheduler is going to walk the topology starting here. If it can find resources for the thread to run on node group 1, it's going to execute it there. It's going to dispatch it there. If not, it's just going to go up, look for resources in node group 5, which, if you remember, has not just node 0, but node 3 and node 1 as well. So it has more resources as you go up into the topology. If it finds resources in node group 5, it's going to dispatch the thread there. If not, it's going to go up to the root LGroup, which has all of the resources in the system, and it's going to dispatch it there. This goes for both the dispatcher and the virtual memory subsystem. So it's when the kernel dispatches a thread, or when the kernel goes out to steal a thread from another CPU and look for resources to it, or when the kernel is allocating a page, it's going to consult this topology to know where to get resources from. So how the scheduler does this? MPO went back into Solaris in Solaris 9, so it's something that's been around quite a while. And back then, one of the changes they made was to create the concept of the home LGroup. So every time you create a thread, that thread has a home LGroup now. And that represents the LGroup in which the thread was created and the LGroup in which you expect the thread to allocate its resources. So it will always try to dispatch the thread to that home LGroup, always. It's always going to try to load balance the threads within the CPUs in that LGroup. So for instance, if you have an LGroup with 4 CPUs, it's going to first try to load balance within that L group, and then farther away. And as I said, it's going to use the topology to dispatch to or steal from. The VM subsystem implemented two policies. The first one is called the first touch policy, which means, let me just go back a little bit. When you do a malloc, a virtual memory allocation call, the kernel doesn't back that memory with physical memory until someone touches it, until some thread actually accesses it and touches it. So until then, it's just virtual memory. When someone accesses that thread, actually touches that space, the kernel is gonna look for which L group it's running, what's the home L group, and what's the policy. If it's first touch, then it's gonna allocate from the faulting thread's home L group. Faulting as in you first touch. It's the first time you're touching a virtual memory space. You might cause, if you're allocating memory, you're gonna cause a page fault, and so forth. It's a default for private memory. And there's also the random policy, which it's a default for shared memory, and it's going to spread memory. If you're allocating a lot of memory from one thread, and that's shared memory, and you expect that memory to be accessed by multiple threads, those multiple threads can be running on, or can run on different nodes. So you don't want to concentrate that memory within one node. You want to spread that memory across all nodes and hopefully take advantage of locality. And it's the default for shared memory. So besides modifications to the kernel, there's an API called liblgroup, which you can use to both observe and optimize the performance for your application on NUMA machines. It's pretty simple. It works with cookies. Since the topology can change in the case of a DR event, a dynamic reconfiguration event in Spark, it usually not, it works with cookies. You take a snapshot of the topology, and then you walk that snapshot, and you observe your system and your application. So you can use that to both discover the contents of an L group and learn about the behavior of your application. And you can also change the affinity of a thread for an L group. I'm pointing out here that affinity is different than the home L group because the home L group would only change if you go into using one of the other tools that I'm going to talk in this next slide. The only way to change the home L group is using one of those tools. Affinity is a concept of, oh, this thread has a behavior, has a local behavior. It's not going to move, or this thread's going to move only on these L groups, or this thread's going to move all over the place. So that's the policy you can change. There's also meminfo. A syscall, you can get some information about the memory on your machine. You can use madvise or this shared library, madv.so.1, to change the behavior of your application. For instance, all of these advices here you can use it with both madv.so.1 or through the liblgroup. So you can say that all my threads are going to behave randomly, so spread it around, give it, allocate memory from all over the place, or it's sequential, or you have, many threads accessing the space that I'm allocating. There's liblgroup, there's LGroup info, which displays information about both the hierarchy and the specific L groups. I have some examples on the next slides. PO group you can use to observe and affect home L group and thread affinities. That's the command I told you about that you can use to change the affinity of a home L group, affinity of a thread, sorry. And pmadvise, which is the same thing as madvise, only that if you're using a syscall, you can do it for inside your code. And if you're using pmadvise, which is a command line tool, you can only do it to an entire process. So this is an output of LGroup info for a NUMA machine, so a non-NUMA machine, my laptop, for instance. It's going to print out the CPUs it has. So here it has 2 CPUs. It's a dual-core machine. So much memory, how much is allocated, how much is free, the load, and it's going to print out this kind of cute little matrix of latencies. So it's just a NUMA machine. There's no latencies involved here. Now, if you go to a 2-node NUMA machine, LGroup info, it's going to show it both nodes, how many CPUs they have, the number of the CPUs, the ID, the latency to access those nodes, and then as you go on, the matrix becomes a little more evolved. So you can see here, LGroup 0, this is root LGroup. It contains all the resources. So if you're accessing stuff on LGroup 0, you have the highest latencies in the system, in this case 96. But if you're accessing from LGroup 1, which has CPU 0, to LGroup 1, you're going to have just 59, which is a number for latency. And it's the same for everything on the diagonal. So things start to get a little interesting. This is I remember which model, maybe an X4500, I'm not sure. This is an 8-node, not so dual-core machine. So you can see how things can get quite big here. But still, you see that if you're accessing stuff on LGroup 0, the root LGroup, you still have the highest latencies around. If you're accessing information from LGroup to the same LGroup, you have the lowest, the local access I was telling you about. So this is a 8 CPU machine, so it goes as high as 8 here, and then things start to get a little different. So how does the OS finds out that you're running on a NUMA machine, right? As far as the OS is concerned, it's a hardware. You have to identify both the CPU, the resources, the topology. Solaris has 3 different implementations. Before build 88 here, for AMD Opterons, we used to probe the PCI space register. This is the North Bridge register, which contain information about the node topology, the latencies, and everything. You could also probe memory, which really doesn't do, because if you're going to probe memory for a system to find out the topology, you might end up probing from position 0 to 2 on 64, which is going to take a while. Starting with Nevada build 88, we're implementing the ACPI tables, which contain 2 tables, the SRAT and the SLIT. This started as a Microsoft and HP thing, and then evolved. Whoops. And it ended up evolving, and now everyone is pretty much compliant with. It's just tables in the BIOS in the ACPI which contain information about this. It was implemented in build 88, which is not so far ago, but it has some gotchas. For instance, because this is BIOS, this is something that the vendors have to implement. And not always the vendors provide this information. So you could have some really weird numbers here. But fortunately, we implemented some routines to verify the value. So in the worst case, you're just going to have a NUMA machine instead of a NUMA topology, which is better than nothing, right? So I wanted to show a little bit of the implementation. This is something I did last year while I was in college, which explains why it's kind of old. It's build 65. But I was implementing a bunch of things here, and I kind of got tired of going back and forth in the code, and I'm not a big fan of cscope, to be honest. So hopefully this is going to come up. So just to stress this part over here, this is work in progress. This is somewhat incomplete. This is something that I did for myself in college that I eventually use. These are diagrams of some MPO-related portions of the kernel. So if you take a look at the main function in the Solaris kernel, this is pretty much what it does from start to bottom. So you can see it's a lot of stuff. There's some stuff missing here, but it's relatively complete. And again, this was based on build 65, so it's kind of old. And you can see right here that one of the first things it does is run this routine called LGroup setup, which does a lot of other things. And my idea here was to implement as many as these diagrams to contain some, not just comments, but some information that you can actually just look at it and see what it means. And this is on my blog. If anyone is interested, this is the URL. So just to show you again another peek at the implementation. This is a routine that it's called to choose the L group from which to run. So the kernel is going to call this routine providing a thread and a CPU partition, and it's basically going to go have a look at the policy. Depending on the policy, it's going to look for space in different nodes. If the scheduler wants to move a thread, again, it's kind of similar. It's going to provide a thread, an LPL, which is a structure that I'm not going to talk now, but and then it's going to go through again the policies. Oh, none of this one. So you can see, for instance, it's taking into account the load average for the nodes. Then it's going to start looking. I'm not seeing something here, but let's just move on. The scheduler is implemented under user source disp, if you want to take a look at it. Then changes to the VM subsystem. I think the most interesting bits here are these two routines. So the kernel has two lists for pages. The kernel not only allocates memory, but it also allocates pages. So it has a free list and a cache list. And these routines are used to allocate pages from those two lists. And if you go to those routines, you're going to see that one of the things it does is first, well, the routine has as an argument an L group. It's going to check if the L group exists. And then somewhere here, it's going to start an L group cookie. And there's a routine called over here that, oh, okay. So L group mem node choose. This is a routine and it's going to choose from which memory node to allocate memory. So you can see that changes to support the L group topology were made inside the kernel at different points. So this is, I guess, the most interesting part, at least for me. We've been seeing a lot of different things, both in hardware and in the industry. So what do we do about virtualization and NUMA machines? Okay, if you have an XVM server running, I don't know how many instances, which side is optimizing for NUMA machines? Is the server, is the host, or is the guest? Well, right now, none. There's no optimizations for NUMA in Xen. As far as I know, none in VMware or any of the other major virtualization systems. So if the host is not aware, there's nothing you can do, because the host is not exporting NUMA stuff to the guest. If it is, it can either export the characteristics and hope that the OS does something about it. If it doesn't export, then it's got to do something by itself. But like I said, none of the existing systems actually do something. And then there's I/O locality, which is very interesting. We're starting to see machines with topologies like this. So you not only have different latencies to access memory in different nodes, you actually have different latencies to access I/O or devices. So for instance, you have one cost of accessing I/O from this node, then accessing this disk from this node, right? So what we do in this situation, we move threads around. Okay, we move the application, we move the kernel, we move the buffers, the DMA subsystem. What? This is something we're still working on, and still something we need to figure out. And again, there's NUMA pretty much everywhere now. So both Sun, AMD, and Intel have processors and interconnect systems. All of these manufacturers and even more all offer NUMA machines. We got NUMA and CMT now. We got increased CMT density. We got machines with multiple cores, multiple threads. What do we do in that situation? Do we have to optimize something? This is hardware sharing relationships that are important for the performance of both the kernel and the user application. So what are you going to do about it? Are we going to restrict the threads to run at a specific LGroup because that LGroup has so many cores? Or are you going to let the threads run around the system, taking resources and possibly trashing their performance? So different topologies like this one. This, if I'm not mistaken, is an X4600. Each node can access 3 other nodes. So for instance, this guy right here, node 3, can access node 2 and node 0, and this disk, for instance. So things tend to get a little complicated. Also, there's observability. I mean, most of these manufacturers, AMD is a good example, they implement a lot of registers in the interconnect to show the ratio of transfer and how much data is actually being transferred. If you're going to look at performance for a NUMA machine on just MP-stat or PR-stat, it might not show you what the interconnect is doing. So you're going to see a lot of I/O, you might see a lot of activity, but you don't know how much the interconnect is actually being used. So this is something we have to support too. And then there's power management, which NUMA is just another case of it. What do you do with performance and power management? Both of them are conflicting. If you want power management, you have to turn down cores. So the question with NUMA machines here, one of the questions could be, okay, so I got an 8-node machine, multiple cores per node. Am I going to shut down some of the nodes to save power, or am I going to shut down multiple cores across the system to save power? What's the best solution here? So these are all questions we're working on. We don't really have the answer for all of them, but we do have a few. So if you have any questions, these are the communities that we participate on. There's the performance community in OpenSolaris. There's the NUMA project. The Tesla project is the power management project for OpenSolaris. And again, if you're interested in participating or just getting more information, you can visit those web pages. We have a bunch of documentation, and we have loads of slide sets, if I'm not mistaken. And if you just pop up in the alias and ask a question, I'm pretty sure everyone will be more than happy to answer. So thank you. That's about it.
Any questions? Any questions?
I want to ask if developer can specify M advice for one particular allocation, not for the whole process, but for some of the allocations.
I'm sorry, could you turn it a little bit higher? Cause
I want to, yeah, much better, thank you. I want to ask if developer can specify advice for one particular allocation in program, not for the whole process, but
right.
for some of them.
Right, then you can use LGroup over here. You can use pretty much any of these advice. You can provide advice for a shared region of memory. There are some routines on LGroup. If you just go to the man page, it's going to list all the routines, and you can do that. You can specify for a specific thread. In the case of the dispatcher, if you want the thread to stay at specific nodes or have a certain behavior, or you can specify a policy for a memory region.
Any more questions?
Just a small question. I'm looking at this advice. Are there any graphics where you can see how does the 4600 behaves when you change the policies and run some program with multiple threads? How it affects the performance, if it's random, if it's sequential, or if it's the normal one?
Well, it depends on your application. I mean, what kind of application you're talking about?
I'm just thinking, like visualizing this stuff. So having an application with 100 threads, doing Fibonacci or whatever,
yeah.
and then running it against different policies, and just seeing how it affects the results.
Yeah, it depends on both. You know, that's a good test application, but it depends on how CPU intensive your application is and how you're going to spread them around. If you do a random, if you use the random policy, provide a random advice, the system is going to spread the pages around the nodes. So if you do that for both pages and both threads, you're going to have a good separation of threads and a good load balance. So that would probably be what you want to do.
Thanks.
Anything more? I can't see any questions, so we have a break up to 3:15, and then we'll be back for the last two sessions. Thanks. Thanks, Rafael.
Thank you.